I'm Sherry LeCain, and my partner is Alexa Lockhart.
For our final project, we decided to experiment with differing chemical reactions and physical reactions by constructing a volcano. When constructing an organic volcano, what ratio and chemical compounds will make the most successful volcanic reaction eruption? And our other investigative question was, does the other ingredients contained in a ketchup bottle delay the chemical and physical reactions of the vinegar that is in ketchup mixed with baking soda when compared to the mixture reaction of distilled vinegar with baking soda? Our materials, we used great value baking soda, NaHCO3, sodium bicarbonate, Del Monte ketchup, which is a mixture of multiple substances. The main ingredient is lycopene, which is actually responsible for its red coloring and commonly found in tomatoes. And the reaction is caused by the diluted acetic acid, which is the vinegar inside the CH3COOH. We also use distilled vinegar, which is more of a purified vinegar, which is the acetic acid. And then we also used our common materials such as beakers, ruler, cups, simulation volcano, a sink or a tarp to control our mess, a timer to time the volcano reaction time, and a scale to measure prior and after the reaction.
Already, I was wanting to go over the molecular compounds. So the first compound we have is acetic acid. It's a covalent bond, and you can see the structure there below. The molecular formula is C2H4O2 or CH3COOH. The molecular weight of acetic acid is 60.05. The next compound we used was sodium bicarbonate. It's an ionic bond, and there's the structure below. The molecular formula for sodium bicarbonate, or also known as baking soda, is NaHCO3 or CnAO3. The molecular weight of this is 84.007.
While mixing NaHCO3, also known as baking soda, with CH3COOH, it will result in carbon dioxide and water. Here are a few Lewis structures. The molecules rearrange and create liquid and a gas. The powder and the liquid mixed formed, as you can see, carbon dioxide, CO2, and water, H2O liquid, as you can see, is the two oxygen molecules with the carbon, and for the carbon dioxide, the two hydrogen models with the oxygen for water. Vinegar is actually a covalent bond, and baking soda is a ionic compound. For our tables, we have trial 1, which is the Del Monte ketchup and great value baking soda. So as we said before, the vinegar in the ketchup is what causes the reaction with the baking soda. And so as you can see by reading this table, our 1-to-1 ratio, which was for trial 1, had a heavier reaction weight, had a higher height reaction, a longer reaction time, and it had a better fizzle. It wasn't exactly an eruption, but it was a lot more progress than the other. For table trial 2, we used this distilled vinegar and great value baking soda. So as you can see by reading this table, we once again had a better trial when we used a 1-to-1 ratio, which was for trial 2, under trial 2. So the 73 milliliters and 73 grams, we had a heavier reaction weight afterwards, which means more substance molecular weight left behind. However, the reaction height was 2 inches higher. We also had a 30-second longer reaction time, and we had a way better eruption. For the thermodynamics of this particular experiment, for the chemical properties, the thermic reaction of sodium bicarbonate, baking soda, mixed with the vinegar resulted in entropy. It was endothermic, and it was parallel phenomena to the second law of thermodynamics. The second law informs us how heat is lost in conversion, so energy is presumably less than the initial state. Thus, with the thermic reaction of NaHCO3 sodium bicarbonate with CH3COOH, otherwise known as vinegar, entropy occurs and creates an endothermic reaction due to the atoms having to rearrange and consume energy. Thus, the entropy of surroundings decreases due to the excessive energy needed to separate the baking soda and the vinegar. Otherwise, the mixture feels cold to the touch. So this happens because the mixture must break apart and reformulate together to create a new molecular bond, resulting in a positive delta H and a negative delta S.
Ready? Then we went into the math side of it. So when we first started with our vinegar, we had measured it in milliliters and we needed to convert that into grams. So 1 milliliter of vinegar is equal to 0.972 grams of vinegar. So in our trial where we had 75 milliliters of vinegar, that came out to be 72.9 grams of vinegar. And you can see in that first top right corner that we had to solve to find out how much acetic acid was in that much vinegar, and it came out to being 3.65 grams of acetic acid. And then we had to do the same thing for the second measurement of vinegar, and we got a total of 3.55 grams of acetic acid for that amount of vinegar we used. Then we had to use stoichiometry to convert it into moles and find out how many moles of CO2 we had. So when we plugged in 3.65 grams of acetic acid, at the end we came up with 0.06078 moles of CO2. And then when we had plugged in 3.55 grams of acetic acid and did the math, we came out with 0.05911 moles of CO2. Next, we had to calculate the baking soda. So this is the baking soda we mixed with the vinegar. We had 63 grams of baking soda, which comes out to 0.7499 moles of CO2. Then we had 73 grams of baking soda, which came out in the end to 0.8689 moles of CO2. Then when we did our ketchup experiments, we had to find the amount of acetic acid that was in the amount of ketchup we used. So because ketchup is a more diluted form of acetic acid, there was not as much in there. So you can see the final number for our two trials were for the 72.11 grams is 0.432 grams of acetic acid. And then for the 77.95 grams of ketchup, there was 0.467 grams of acetic acid. Then we had to do again the stoichiometry below to convert it into moles and then find out how many moles of CO2 we had. So for 0.432 grams of acetic acid, we came out to getting a total of 0.007194 moles of CO2. And then for the 0.467 grams of acetic acid, we had gotten 0.007776 moles of CO2. Then when we mixed the baking soda with the ketchup, we had used 72.2 grams of baking soda. At the end, that was 0.8594 moles of CO2. And then for the mixture with 34.5 grams of baking soda, it came out to 0.4106 moles of CO2. Finally, we wanted to go into NGSS and how our experiment meets these standards. So the first one we related it to or saw was K2 ETS1, which is engineering design. The first one is K2 ETS1-1. Ask questions, make observations, and gather information about a situation people want to change to define a simple problem that can be solved through the development of a new or improved object or tool. K2 ETS1-2, develop a simple sketch, drawing, or physical model to illustrate how the shape of an object helps its function as needed to solve a given problem. K2-ETS1-3, analyze data from tests of two objects designed to solve the same problem to compare the strengths and weaknesses of how each performs. The science and engineering practices that go along with this engineering design are asking questions and defining problems. So you would ask questions based on observations to find more information about the natural and or designed worlds, K2-ETS1-1. Then also that would mean we would define a simple problem that can be solved through the development of a new or improved object or tool, and that correlates to K2-ETS1-1. Another science and engineering practice was developing and using models. So we would develop a simple model based on evidence to represent a proposed object or tool, and that corresponds to K2-ETS1-2. Then the final science and engineering practice for engineering designs is analyzing and interpreting data. So we would analyze data from tests of an object or tool to determine if it works as intended. K2-ETS1-3. The DCIs that follow it along with this is ETS1A, defining and eliminating engineering problems, ETS1B, developing possible solutions, ETS1C, optimizing the design solution. And then the cross-cutting concepts are structure and function. The shape and stability of structures of natural and designed objects are related to their functions, which corresponds to K2-ETS1-2. All right, then we went on to 2-PS1, matter and its interactions. So this is a second grade level, matter and its interactions. 2-PSI1-1, plan and conduct an investigation to describe and classify different kinds of materials by their observable properties. 2-PSI1-2, analyze data obtained from testing different materials to determine which materials have the properties that are best suited for an intended purpose. The science and engineering practices that go along with this are planning and carrying out an investigation, which means we would plan and conduct an investigation collaboratively to produce data to serve as the basis for evidence to answer a question. 2-PSI-1. Another is analyzing and interpreting data. So we would analyze data from tests of an object or tool to determine if it works as intended. 2-PS1-2. Constructing explanations and designing solutions is another one of the science and engineering practices. And this is making observations firsthand or from media to construct an evidence-based account for natural phenomena. 2-PS1-3. Engaging in arguments from evidence means we are going to construct an argument with evidence to support a claim. 2-PSI1-4. Then the final science and engineering practice is connections to nature of science. So that means science models, laws, mechanisms, and theories are explained. So scientists search for cause and effect relationships to explain natural events, which corresponds to PS1-4. The disciplinary core ideas for this are PS1A, structure and properties of matter. So this means that different kinds of matter exist, and many of them can be either solid or liquid depending on temperature. Matter can be described and classified by its observable properties. 2-PS1-1. And then finally, we are looking at the cross-cutting concepts. So we see patterns and cause and effect. So patterns in the natural and human designed world can be observed, and then events have causes that generate observable patterns, and also simple tests can be designed to gather evidence to support or refute student ideas about causes. The final NGSS standard is 5-PS1, structure and properties of matter. So these are 3 through 5 standards that will build upon their previous K-2 knowledge. So 5-PS1-3, make observations and measurements to identify materials based on their properties. 5-PS1-4, conduct an investigation to determine whether the mixing of two or more substances results in new substances. So the science and engineering concepts or science and engineering practices that go along with that are developing and using models. Again, building upon their K-2 experience, they'll develop models to describe phenomena. The next one is planning and carrying out investigations. So these students should be able to conduct an investigation collaboratively to produce data to serve as the basis for evidence using fair tests in which variables are controlled and the number of trials considered. It is also to make observations and measurements to produce data to serve as the basis for evidence and for explanation of a phenomenon. 5 PS 1-3. Another SEP is using mathematics and computational thinking. So this is where students can measure and graph quantities such as weight to address scientific and engineering questions and problems. The disciplinary core ideas that go along with these standards are PS 1A, structure and properties of matter. Measurements of a variety of properties can be used to identify materials. At this grade level, mass and weight are not distinguished, and no attempt is made to define the unseen particles or explain the atomic scale mechanism of evaporation and condensation. PS1B, chemical reactions. When two or more different substances are mixed, a new substance with different properties may be found. And then finally, our cross-cutting concepts, we have cause and effect. So the cause and effect relationship are routinely identified, tested, and used to explain the change. And scale, proportion, and quantity. Standard units are used to measure and describe physical quantities such as weight, time, temperature, and volume. This corresponds to 5 PSI 1-2 as well as 5 PSI 1-3. Then finally, there's a connection to the nature of science. So as well as in the K2 experience, that means these kiddos at the grade level will have scientific knowledge that assumes an order and consistency in natural systems. So science assumes consistent patterns in natural systems. In conclusion, we found out that a 1-to-1 ratio was best for both trial 1 and trial 2. So when we had used ketchup versus vinegar, both 1-to-1 ratio came to the best result on either trial. The other ingredients present in the ketchup bottle didn't cause a delay in the reaction, but it did cause the outcome to be less pressurized, resulting in less height, a quicker stop time, and more foam or fizzle rather than being an eruption that came out of the volcano.
So to answer the conclusion questions that result back to the anchor phenomena. So in constructing an inorganic volcano, what ratio and chemical compounds will make the most successful eruption? So like she said, 1-to-1 ratio was best for both trial 1 and 2. However, the height of the eruption was only 1 centimeter higher than the second trial, which had a 37.7 gram difference in baking soda prior to the reaction. The second trial had a 37.7 less grams of baking soda and a 5.8 grams more of ketchup, so vinegar. The vinegar and ketchup. We felt that the ketchup wasn't the best go-to for making an erupting volcano because we only saw lots of fizzling, and the fizzling was rather stagnant, but the first 50 seconds for the first time and only 20 seconds the second time. Thus, we realized from this experiment that both the vinegar and ketchup mixed with baking soda were as important as each other, and so was the baking soda with the vinegar. So that's how we got the 1-to-1 ratio. And if you want to make the best volcano, we suggest using vinegar and baking soda, which is trial 2, the 1-to-1 ratio.
And then this is all of the references we used in this presentation. Thank you so much for your time.
Thank you.